This is a supplementary video for our short paper on a formative study we conducted using an HMD simulator we developed as a design probe. In this video, we primarily aim to provide a walkthrough of the HMD simulator tool. For other study details, please refer to the paper. As a design probe, the current implementation prioritizes breadth of features for exploration and reflection rather than usability. Let's now walk through some of these features. The main goal of the tool is to simulate how an HMD renders stereo images based on position and orientation of a skeleton 3D model of an HMD. The central feature is the visualization of stereo frustums and the rendered images, one for each eye. This lets learners see the otherwise unseeable graphical processes behind the scenes. For example, they can now see how the overlapping frustums form a shared binocular region, which creates depth perception and the sense of immersion. A core feature of the tool is the ability to adjust key HMD parameters such as the interpupillary distance or IPD. Here we can see how changing the IPD affects the view frustums and the rendered stereo images. As another example, adjusting the eye relief parameter changes the distance between the eyes and the lenses, as you can see in the HMD skeleton model here. We can similarly observe changes in the view frustums and rendered images. To observe how the HMD position and orientation influence the rendered images in real time, users can rotate and move the virtual HMD. Here I am using the WASD keys and the mouse to move and rotate the HMD, and we can see how the view frustums and rendered images update accordingly. As a way for participants to see how learners can customize their learning contexts, the current version includes a scene switcher that allows learners to explore different 3D environments. This includes the ability to import and render modern 3D reconstructed Gaussian splats as shown in these sample scenes. This points to future potential for custom user-defined scenes. To envision how such tools can be used for embodied learning, there is a VR mode in the current version that allows users to experience their parameter configurations in a real enclosure such as a Google Cardboard. Here I'm launching the tool on my iPhone and launching the VR mode. This way, learners can experience the real-world immersion effects, for example, when the parameters are adjusted differently relative to the actual hardware attributes. The HMD simulator is open source, and study participants were also encouraged to explore the codebase and think about how it can be adopted and extended for other educational contexts. In small group workshops, the simulator was used as a design probe. Participants explored conventional learning materials such as slides and videos, and compared them to hands-on interactions with the HMD simulator. They were encouraged to think aloud and later responded individually to open-ended questions about their experiences and perceptions. The group format supported both personal reflection and discussion. Our analysis showed that interactivity made the experience highly engaging, sparking curiosity and experimentation. Yet, participants emphasized that without clear connections to conventional materials, interaction risked lacking purpose. Real-time feedback, however, reduced cognitive load, opening space for reflection and critical inquiry. For the complete findings and design considerations, please see our paper. Thank you for watching.